Deploying apps in seconds instead of days, that's what Docker does. But most tutorials only scratch the surface, missing almost 70% of what Docker can really do. Today, we're fixing that. In this video, you'll learn everything, from your very first container to advanced orchestration. So grab a coffee, because by the end of this, you'll know more than 99% of developers about Docker. Let's dive in. First things first, what is Docker? Docker is a platform that lets you package your application and all its dependencies into something called a container. Think of a container like a shipping container for code. Everything your app needs is inside. How's that different from a virtual machine? Well, a VM includes a full operating system, which makes it heavy. A container, on the other hand, shares the host OS kernel, making it lightweight and super fast. So, Docker equals lightweight, isolated, portable environments for your apps. And that's why it's a game changer. Next up, the Docker engine. This is the heart of Docker. It has three main parts. 1. Docker daemon. This is the background service that actually runs your containers. 2. Docker CLI, the command line tool you'll use to talk to Docker. And 3. Docker API, which lets other apps talk to Docker programmatically. So when you type docker run in your terminal, the CLI talks to the daemon through the API and boom, your container starts. Before we do anything fancy, we need Docker installed. Go to docker.com, and if you're on Windows or Mac, download Docker Desktop, and if you're on Linux, follow the installation commands from here. After that, check your installation with docker -- version. If you see a version number, then you're ready to start. Now that Docker is installed, let's run our very first container. Open your terminal and type docker run hello world. This downloads a tiny image from Docker Hub and runs it. If everything works, you'll see a message saying hello from Docker. This confirms that Docker is working fine on your system. So what just happened? You ran a container based on a Docker image. Think of an image as a blueprint for your app. It contains everything needed: the code, libraries, and environment. When you run docker run, it pulls the image, creates a container from it, and runs it. Remember this: image equals blueprint, container equals the running instance of that blueprint. Where do these images come from? Most likely from Docker Hub, which is the official image repository for Docker. It's like an app store for containers. You can find thousands of ready-to-use images there. Pro tip: always check if the image is official or verified before using it, for security reasons. Alright, now that we know about Docker Hub, let's talk about pulling images manually. The command is docker pull followed by the image name. For example, to pull node.js, type docker pull node. What happens here? Docker checks if the image exists locally. If not, it downloads it from Docker Hub. Why would you pull an image manually? Well, sometimes you want to download the image first, without running it immediately. Pro tip: you can also specify a tag like nginx:1.23 to pull a specific version. If you don't, Docker pulls the latest tag by default. So remember this pattern: docker pull equals download only. Running it comes next. Now, let's run something real: a Node.js environment inside a container. Type this command: docker run -d -p 3000:3000 node. What does this do? Docker run, it tells Docker to create and start a container. -d runs it in detached mode, meaning in the background. So, if you close the terminal, the container is still running. Without this, the container would stop when you would run another command in the same terminal, or when you would close it. -p 3000 : the 3000 maps port 3000 on your machine to port 3000 inside the container. The port on your machine can be any port, but the container must be kept to 3000 as expected. Node: it's the image we're using. After running this, you've got a container ready to use. Pro tip: if you want to run an interactive Node.js read eval print loop inside the container, you can use docker run -it. node. This drops you into a Node.js shell right inside the container. Pretty cool, right? You've got containers running, but now how do you check them? Use this command, docker ps. This lists all running containers: container ID, image, command, status, ports, and name. If you want to see all containers, including stopped ones, add a -a. Docker ps -a. Pro tip: every container has an auto-generated name if you don't provide one. They're usually fun combos like bold solder or any kind of random name. So don't worry if you see anything unfamiliar, because it only means you did not provide the container a name and it received a random one. Another cool trick: if you only want the container IDs, use docker ps -q. This is super useful when you need to script things like stopping multiple containers in one go. So the three variations are docker ps for running, docker ps -a for all, and -q for IDs only. You've launched a node container, but now how do you stop it? Use this command, docker stop followed by the container ID, or you can use the container name instead of the ID. Docker stop followed by whatever name the container got. Pro tip: you can stop multiple containers at once by listing them like this: docker stop ID1, ID2, ID3. Now, what if you want to remove the container completely? Use docker rm followed by the container ID. Here's the catch: you cannot remove a running container, so always stop it first. Want to remove all stopped containers in one go? Use docker container prune. It'll ask for confirmation, then clean up all the unused containers. So remember this cleanup flow: stop, remove, prune. Let's talk about port mapping. When you run a container, it lives in its own network namespace. That means its ports aren't exposed to your host machine unless you tell Docker to map them. The -p flag does exactly that. For example, docker run -d -p 8080:3000 node. Here, the first number, 8080, is the host port. The second number, 3000, is the container port. So any traffic coming to localhost :8800 on your machine gets forwarded to port 3000 inside the container. Why does this matter? If your Node app is listening on 3000, you can access it from your browser at port 8080. Pro tip: you can map multiple ports by adding more -p flags, like P8080:3000, P5000: Next, let's break down the -d flag, detached mode. We already talked about it, but let's have a better understanding. When you start a container, by default, it runs in the foreground, meaning your terminal is attached to it. You'll see the logs right there, and you can't run any other commands until you stop it. Detached mode solves this by running the container in the background, freeing up your terminal. So when you do docker run -d node, you can keep working while the container runs in the background. Pro tip: want to see the container's logs later? Use docker logs followed by the container ID or name. And if you want to attach back to it, WSE, docker attach container ID or name. Sometimes your app needs environment variables like API keys, database, URLs, or custom configurations. With Docker, you can set these using the -e flag. For example, docker run -d -e node env equals production node. Here, we're telling the container that node env is set to production. Why is this important? Because many apps behave differently based on environment, like development versus production. Pro tip: you can pass multiple variables like this: docker run -d -e, node env production -e, port 3000 node. Want to load them from a file? Use -env file followed by the file location. So remember, -e for individual variables and -env file for bulk. Sometimes you need to get inside a running container, maybe to debug or check logs. For that, we use docker exec. The full command looks like this: docker exec -it followed by the container name or ID bash. Here's what it means. Exec. It run a command inside an existing container. Minus it. Interactive and terminal mode. Bash. It's the shell we want inside the container. Depending on the image you're using, it might not have bash by default, so you can use sh instead. Docker exec minus it container name sh. Now you're inside the container like it's a mini virtual machine. Pro tip, you can also start a node read eval print loop inside the container with docker exec -it followed by the container ID node. Super handy for debugging live. So far, we've been running pre-built images like Node. But what if you want your own app inside a container? Enter the Dockerfile, the blueprint for building your own images. A simple Docker file for a Node.js app might look like this. Let's break it down. From Node:18. It start from the official Node image. workdir/app. It set the working directory inside the container. Copy .space. It copy everything from your project into the container. Run npm install. It install dependencies. cmd node app.js. It's the command to run when the container starts. This is the core structure you'll see in most Docker files, but it can get much more complex than this, as we will see later. Once you have a Docker file, you need to build the image. The command is docker build -t, followed by any name I want to give it to the image, then a dot. Here's what it means. Docker build. It start building an image, -t. App name, it give the image a name. Dot is used for build from the current directory. Docker reads your Docker file, executes each instruction, and creates a new image layer by layer. Pro tip, use descriptive tags like myapp:\v1 instead of just myapp. It makes versioning easier. If no tag is provided, the built image will always have the tag latest. And if the same image is built twice, the old one is losing the tag and assigned to the new one. Before you hit build, here's a time-saving tip. Use a .dockerignore file. It works just like gitignore. You list the files and folders you don't want copied into the image, like node modules, git directory, logs, or temporary files. Why? Because unnecessary files make your image bigger and slower to build. Always use this to keep your images lean and fast. By default, when a container is deleted, all its data is gone. That's fine for stateless apps, but what about databases or files you want to keep? That's where Docker volumes come in. Volumes let you persist data outside the container, so even if the container is removed, your data stays safe. You can create a volume with docker volume create, followed by any volume name you want to give it, and use it like this. Docker run -d -v volume name : /data node. Here, /data is the path inside the container where data is stored. Pro tip, volumes live in Docker storage area, so they're managed by Docker and easy to reuse across containers. Sometimes you don't just want to persist data, you want live sync between your machine and the container. That's where bind mounts come in. The syntax is docker run -d -v path on the host : path on the container node. For example, docker run -d -p, then the ports and -v with the paths, then container name. Here's what happens. Your current directory, pwd, on your machine is mounted into app inside the container. This is amazing for development because changes on your host are instantly reflected inside the container. Pro tip, always mount only the directories you need, not your entire system, for security and performance reasons. Need to copy a file to or from a container? Use Docker CP. For example, to copy a file from host to container, Docker CP file name container ID : container location. And the other way around, Docker CP container ID : container location, then host location of the file. This is super handy for grabbing logs, configs, or results without mounting a volume. So remember, Docker CP is your quick transfer tool between the host and container. Sometimes you need all the juicy details about a container, like its IP address, mounts, environment variables, or the exact image it came from. For that, Docker gives us the powerful command, docker inspect container name or ID. This command returns a lot of information in JSON format. Now think of it like the container's full report card. From network details to volume mounts, it's all in there. Here's a quick tip. If you're only looking for something specific, like the IP address, you can use filters with dash dash format. For example, this one. That's how you go from drowning in data to grabbing just what you need. Containers log mostly everything that happens inside them, and checking those logs can save you hours of troubleshooting. To see logs from a container, use docker logs container name or ID. This will show everything that container has output to the console. If you want to see the logs live as they are happening, add -f for follow mode, or add --follow. This is super helpful for debugging. You'll see the logs streaming in real time, just like tailing a log file on a server. And here's something extra. You can even limit how many lines to show with --tail. For example, docker logs --tail 10. So whenever something goes wrong, logs are your first best friend. Containers are not eternal. Sometimes you need to stop them, restart them, or bring them back to life after a change. To stop a running container, use docker stop container name or ID. If you need to restart it immediately after, simply run docker restart container name or ID. Here's the key difference. Stopping a container doesn't delete it. The container is still there, like a paused game. You can start it again anytime using docker start container name or ID. Think of it like this. Stop puts the container to sleep, start wakes it up, and restart gives it a quick nap and wake up call in one go. Sometimes you don't just want to stop a container, why you want it gone completely. To remove a container, use docker rm container name or ID. But remember, you can only remove stopped containers. If it's still running, you'll get an error. If you want to remove it, even if it's running at -f for force docker rm-f container name or ID. Here's a quick tip. If your system is cluttered with dozens of old containers, you can clean them all up in one command, docker container prune. That will remove every stopped container, but be careful, there's no undo button. Images take up space, and over time, you'll have a lot of them. If you're done with an image, you can remove it using docker rmi image ID, but you can't delete an image if it's still being used by a container. So make sure you remove those containers first. For a full system cleanup, Docker gives you a magic command, docker image prune. And if you're feeling extra brave and want to remove all unused images, add the -a flag, docker image prune -a. This is like a spring cleaning for Docker. Just remember, once you delete an image, you'll need to download it again if you want to use it later. All right, by now you've been working with single containers, and that's cool. But real-world apps usually need multiple containers working together. For example, you might have a Node.js backend, a database like MySQL, and maybe a caching service like Redis. Running them one by one with Docker Run can get messy real fast. That's where Docker Compose comes in. It's a tool that lets you define and manage multi-container applications with a single file and a single command. You create a Docker Compose file that describes your services, and then Docker Compose takes care of starting everything in the right order. Think of it as orchestrating your containers in harmony, like a conductor leading an orchestra. With one command, all your services come alive. So, how does this magical file look? Let's break it down. Older versions of Docker Compose included a version number at the top of the file, but the latest Docker Compose versions have removed this requirement. However, it's still worth mentioning since you might encounter older Docker Compose files that include it. Following that, you'll find a list of services. These represent your containers. For example, you might have a Node app service that uses a Node.js image and a MySQL DB service for your database. Each service can define ports to expose, volumes for persistent data, and networks so the containers can talk to each other. The beauty of Compose is that it creates an isolated network for your app by default. So, your containers communicate easily without exposing unnecessary ports to the outside world. And with volumes, your database data will survive container restarts, which is critical in real apps. In short, services define your containers, networks connect them, and volumes keep your data safe. Now that you've written your Docker Compose, how do you actually run it? You'll mostly use three main commands. Docker Compose up, this starts all your services. Add -d to run them in the background. Docker Compose down. This stops and removes all the containers, networks, and by default, the anonymous volumes created for the project. It only keeps the named volumes. Docker Compose logs. This shows you the combined logs of all your containers, which is super handy when debugging multi-container setups. And the best part, you run all these commands from the directory where your Docker Compose lives. Simple and powerful. What if you need different configurations for development and production? No problem. Docker Compose lets you override configs using multiple YAML files. For example, you might have a Docker Compose for your base setup and a Docker Compose override for your local development tweaks. When you run Docker Compose up, it automatically applies both files, with the override file taking priority. You can even specify custom override files using -f like this. This gives you flexibility without duplicating entire configs. Just override what's different, like environment variables, ports, or volume mappings. It's a clean and professional way to manage multiple environments with Compose. Let's talk about data persistence, because when a container is removed, its data is gone. That's fine for stateless services, but not for databases or apps that store files. Docker solves this with volumes, and there are two main types you need to know: named volumes and bind mounts. A named volume is managed by Docker. You just give it a name, like db data, and Docker stores it in its default location. Simple, clean, and great for most use cases. A bind mount is when you map a specific directory on your host to a directory inside the container. This is awesome for development because changes you make on your machine show up instantly inside the container. So remember, named volumes are great for production where you want Docker to manage everything. Bind mounts are perfect for local development where you need live updates. So far, we've talked about basic volumes, but what if your app needs to store data outside of your single machine, like on a network file system or in the cloud? That's where volume drivers come in. Volume drivers let Docker connect to external storage backends. The most common ones you'll see: NFS, Network File System, for shared storage across multiple servers; AWS EBS, if you're running on AWS and want persistent storage across container restarts. When you create a volume, you can specify a driver like this, which tells Docker to mount an NFS share instead of using the default local storage. The key takeaway: volume drivers make your data portable, persistent, and scalable across nodes, perfect for production deployments. Let's move on to networking. Docker gives you different network modes, and understanding these will make you a pro. Bridge, the default network. Containers, get an internal IP and talk through NAT. Great for most single host setups. Host, the container shares the host network stack. No isolation, just raw speed. But be careful, this removes port mapping and isolation. None, literally no network. Perfect for running a container that doesn't need any network connectivity. Overlay. This is for multi-host communication, like in Docker Swarm. It creates a virtual network across multiple machines so containers can talk to each other even if they're on different servers. So when should you use each? Bridge for normal cases. Host when you need performance and don't care about isolation. None for security or testing. Overlay for clustering. Now, what if you want full control over your container network? That's where custom networks come in. Why would you need this? Two main reasons: to isolate groups of containers and to give containers predictable DNS names. Here's how you create a custom network. Docker network create, followed by any network name you want. Then When you run a container, you attach it with this command. Now, any container in that network can reach web by just using its name and no IPs needed. This is awesome for multi-container apps because you can structure your architecture like a pro. Okay, you've got custom networks, but what if two containers are on different networks and need to talk to each other? By default, they can't because Docker isolates networks for security, but you can connect a container to multiple networks using the following command. Now, DB container belongs to two networks and can talk to services in both. This is useful when you have a shared database or logging service that multiple apps need to access, but you still want isolation between the apps themselves. Just remember, with great power comes great responsibility. Don't randomly connect everything or you defeat the purpose of isolation. Now, let's talk about writing Docker files like a pro. A huge mistake beginners make is building images that are way too big, which cause slowing down builds and deployments. Here are 3 golden rules for reducing image size. Start with a small base image, like Alpine instead of Ubuntu. Alpine is only about 5 megabytes. Combine commands with and so you don't create unnecessary layers. Clean up after installs by removing cache files and temporary data. For example, instead of these 2 lines, you can use it in a single run command. Why does this matter? Smaller images mean faster builds, less storage, and faster deployments. And trust me, in production, every second counts. Here's a real-world problem. Your app needs dependencies to build, but you don't want all those build tools bloating your final image. That's where multi-stage builds come in. The idea is simple. You create multiple stages inside one Docker file. The first stage installs everything for building your app, compiles it, and then the second stage grabs only the output and copies it into a fresh, clean image. For example, imagine a Node.js app. In the first stage, you install Node and all dependencies to build it. In the second stage, you just copy the build files into a lightweight image like node::alpine. The result is a smaller, faster, production-ready image with no extra baggage. And the best part, you don't need multiple Docker files, just one with multiple stages. Containers aren't magic. They can fail even if the process is still running. That's why Docker gives us health check. With health check, you tell Docker how to verify that your container is healthy. For example, you can ping an HTTP endpoint like /health every 30 seconds. If the check fails too many times, Docker marks the container as unhealthy. Why is this important? Because orchestration tools like Docker Swarm or Kubernetes use this health status to restart failing containers or reroute traffic. So, always add a health check in your production images. It's like giving Docker a stethoscope for your app. If you've ever wondered what the difference is between Entrypoint and CMD, here's the deal. Entrypoint defines the main command that always runs. CMD provides default arguments for that command, but they can be overridden when you run the container. Think of Entrypoint as the engine and CMD as the fuel you can swap. For example, Entrypoint node cmd app.js. This means your container will always run node, and by default, it runs node app.js, but you could override app.js when starting the container. If you switch them, things behave differently, so be intentional. Sometimes you need to pass temporary values during the image build process, like a version number or a build flag. For that, Docker gives us rg. You declare it in the Docker file like this, rg followed by the variable name. Then, when building the image, you can override it with the following command. Here's the key. Arg values are only available at build time, not at runtime. So don't put secrets here. It's visible in image history. Use environment variables for runtime configs instead. Tags matter. When you build or pull an image, Docker uses tags to identify versions. If you don't specify a tag, Docker assumes it's latest. But relying on latest in production is risky because it might change without you knowing. Instead, use explicit tags like v1 or 1.00. Even better, follow semantic versioning so everyone knows what version they're using. You can also add multiple tags when building. This way, you can keep latest for convenience but still pin exact versions when deploying. You've built an amazing image locally, but now you want to share it with the world, or at least your team. That's where Docker Hub comes in. Docker Hub is like GitHub, but for container images. To push an image, you first need to log in using Docker login. Then, tag your image properly with your Docker Hub username and the repository name. Finally, push it with Docker push username /myapp:/latest. Done. Your image is now available on Docker Hub and can be pulled from anywhere. Pro tip: never push sensitive data or secrets inside your image. Always keep builds clean and secure. Sometimes you can't use public Docker Hub because of security or compliance. That's where private registries come in, like AWS ECR, Google Container Registry, or maybe a self-hosted GitLab image registry. The concept is the same. You tag your image and push it. But authentication works with cloud credentials. For example, with AWS ECR, you authenticate using the following command. Then you push the image to your ECR repository. The benefit? Your images stay private, secure, and under your control. If you work with multiple Docker environments, like local and remote servers, you'll love Docker Context. It allows you to switch between Docker hosts without constantly setting environment variables. Run Docker Context ls to list all context. Use Docker Context create to add a new one pointing to a remote Docker host. Then switch easily with Docker Context use followed by the context name. From that point on, every Docker command runs on the selected context. Super handy for DevOps and multi-environment setups. Containers are lightweight, but you still need to monitor CPU, memory, and network usage. Docker has a built-in command for this, Docker stats. It gives you real-time resource usage for all running containers, CPU%, memory usage, network I/O. Great for troubleshooting performance issues or checking if a container is hogging resources. For deeper insights, tools like Advisor or Prometheus can give you dashboards and alerts, but Docker stats is a great starting point. Logs are everything when debugging containers, and Docker supports multiple logging drivers. By default, Docker uses the JSON file driver, which stores logs in that format on the host. But you can change the driver to syslog, fluentd, or even send logs to cloud services. You do this when running a container with the flag log driver. For production, use a centralized logging system. Local logs are fine for dev, but in production, aggregated logs are a lifesaver. Want to see what's happening inside your Docker engine in real time? Use Docker events. This command streams live events like container start, stop, network creation, volume attachment, basically the Docker heartbeat. For example, you can see only container start events with this filter flag. This is useful for troubleshooting or monitoring activity in real time. Containers crash. It happens. Restart policies help keep them running automatically. When you start a container, you can use restart flag with policies like no, don't restart, this is the default one. On failure, it restart only if it exits with an error. It will always restart the container. And unless stopped, it restart unless you explicitly stop it. This is critical for production. Never leave containers unmanaged. Docker Swarm turns multiple Docker hosts into one cluster that you can manage as a single system. You get features like service replication, load balancing, and scaling, all using Docker's native tools. Swarm is simpler than Kubernetes, but still very powerful for smaller setups. If you need HA, high availability, and distributed workloads, Swarm is a good starting point. To create a swarm, you start by initializing it on a manager node, Docker Swarm init. This makes the current machine the swarm manager. Then you'll get a command to join worker nodes using a token. From there, you can deploy services that run across the cluster. It's that simple to set up a basic swarm. In swarm mode, you don't run individual containers, you deploy services. For example, Docker service create followed by the number of replicas and the name. This creates a service named web with 3 replicas running Node.js across the cluster. Swarm handles load balancing and failover automatically. You can scale services easily with Docker service scale web equals 5. This is the power of container orchestration, automation, and resilience. If Docker Compose is your local development hero, Docker stacks are its big brother for production in swarm mode. Stacks allow you to deploy multi-service applications, just like Compose, but across a swarm cluster. Instead of Docker Compose up, you use Docker Stack Deploy. The difference? Swarm schedules your services across multiple nodes for high availability and scalability. You still define everything in a configuration file, called a stack file, with services, networks, and volumes. But now, Swarm takes care of load balancing and service distribution. This command deploys your app as a stack named MIAP. Behind the scenes, each service becomes a Swarm service, managed and distributed across the cluster. Think of stacks as Compose on steroids, perfect for production, resilient, and cluster ready. Let's talk about updates without tiers, rolling updates in swarm mode. When you deploy a new version of a service, you don't want all containers to stop and restart at once. That would mean downtime, and nobody likes that. Instead, Swarm gives us rolling updates with the update parallelism flag. Let's take this example and see what happens here. Swarm updates 2 tasks at a time, checks if they're healthy, and then moves on to the next set. Combine that with the update delay flag to pause between updates for safety. This is zero downtime deployment done right. It's like upgrading your app while users keep working, smooth and professional. Hard coding passwords in configs, it's a big security no-no. Enter Docker secrets, your secure way to store sensitive data like passwords, API keys, and certificates. Secrets are encrypted and only accessible to the containers that need them. With this command, now any Swarm service can mount this secret securely at runtime. Inside the container, the secret appears as a file, not an environment variable. Why? To avoid leaking secrets in logs or process lists. Bottom line, use secrets for sensitive data and sleep better at night. Not everything is a secret. Some files, like app configs, aren't sensitive but still need management. That's where Docker configs come in. Configs work a lot like secrets, but they're designed for non-sensitive data like JSON configs or HTML templates. After you create a config inside the container, it mounts as a file in /config/. The beauty? You can version and update configs without rebuilding your images. So remember, secrets for sensitive stuff, configs for everything else. Now let's supercharge your image builds with Docker BuildKit. BuildKit is Docker's next-gen build engine, designed for speed, caching, and security. It allows parallel builds, build secrets, and even inline caching for CI/CD pipelines. To enable it, set the Docker BuildKit variable to 1, then just build an image. With BuildKit, you can do things like secret mounts during build, so no more leaking secrets in images. Smaller images thanks to better caching, or faster builds with concurrency. If you're still building without BuildKit, you're leaving performance on the table. Security is critical, and Docker Content Trust helps you verify the authenticity of your images. What does this mean? It ensures that the images you are pulling or pushing are signed and trusted. Imagine you're deploying to production, and you accidentally pull an image from a random public repository. That image might be compromised. Content Trust prevents that by checking digital signatures. To enable it, set the environment variable for Docker Content Trust to 1. With this enabled, Docker will only pull or push signed images. If an image isn't signed, the operation will fail. This is especially useful for production environments or CI/CD pipelines where security matters. So remember, turning on Docker Content Trust means you trust the source, not just hope for the best. Just because your image works doesn't mean it's safe. That's where image scanning tools like Tryvi and Snike come in. These tools check your Docker images for vulnerabilities. Things like outdated libraries, CVEs, and insecure configurations. Tryvi is super easy to use. You install it and run it with an existing image you have. This will scan the node image for known security issues. Snyk works similarly but integrates really well with CI/CD pipelines and GitHub repos, giving you continuous monitoring. Why is this important? Because vulnerabilities don't care if your app is working. They care about being exploited. Regular scanning keeps you ahead of attackers. Running databases in containers is common, but here's the golden rule. Data must outlive the container. If you simply run Docker, run MySQL, the data lives inside the container. Remove the container, and poof, your data is gone. The solution? Volumes. For example, this will use a volume named dbData, and it maps it to MySQL's data directory, keeping data safe even if the container dies. You can also use bind mounts for development, mapping a local folder to your container. Just remember that in production, named volumes or external storage like NFS or cloud volumes are the way to go. So the takeaway, Dockerizing a database is easy, but persisting its data is non-negotiable. Docker and CI/CD go hand in hand. Why? Because Docker gives you consistent environments from development to production. In a typical pipeline, you might first build your app image in the CI environment, then run tests inside a container. After that, push the image to a registry, and finally, deploy using that image. This guarantees that what you tested is what you deploy. No more, it works on my machine problems. Tools like GitLab CI, Jenkins, and GitHub Actions have native Docker support. You can use Docker in Docker or remote Docker executors to build and test images. The key benefit? Speed, consistency, and portability. Sometimes your container misbehaves and you need to look inside. One quick way to interact with a running container is docker attach. This command connects your terminal to the container's standard input and output. Once attached, you see the container's live output, and you can even send commands if the container supports it. But be careful. Pressing Ctrl+C might stop the container if it's running in the foreground. To detach without stopping it, use Ctrl+P plus Ctrl+Q. For deeper debugging, you might prefer Docker exec in the container, but attach is great for real-time monitoring. Both Kubernetes and Docker Swarm orchestrate containers, but they're like two very different toolboxes. Kubernetes is the heavyweight champion, packed with features like self-healing, scaling, secrets, configs, and a massive ecosystem. It's designed for production at scale with advanced networking and rolling updates. But it's complex. Docker Swarm is lightweight and simple. If you know Docker Swarm feels natural, just a few commands and you've got a cluster. It's great for smaller deployments or when you want simplicity. So the rule of thumb, if you need enterprise-grade orchestration, go Kubernetes. If you want easy mode for clusters, Docker Swarm has your back. So how do Docker containers run on Kubernetes? The truth is, Kubernetes doesn't care if it's Docker or another container runtime, like Containered or CRIO. But you can absolutely deploy Docker-built images on Kubernetes. Here's the workflow. Build your image, then push to registry, and then deploy with kubectl using a deployment manifest. Inside that manifest, you just reference your image and other informations. So the main difference, Kubernetes handles containers at scale, while Docker alone does not. Running Docker as root? That's risky. If a container escapes, boom, it owns your host. Enter Rootless Docker. Rootless mode runs the Docker daemon and containers without root privileges. This isolates your system from container risks. Perfect for dev environments and extra hardening in production. You can enable it using this command. Then start Docker as your user. Keep in mind some features like privilege mode won't work without root. By default, the root user inside a container maps to root on the host. User namespaces fix this by remapping container users to non-root users on the host. You enable it in etc. Docker daemon JSON. Now root inside the container becomes a safe, unprivileged UID on your host. More isolation, less risk. Containers aren't magic. They still rely on the host kernel. SE Linux and AppArmor add mandatory access controls to lock down what containers can do. Docker automatically applies a default AppArmor profile on Linux. You can check it with the following command for SE Linux. Add the :z flags on volume mounts for proper labeling. These controls are your last line of defense against privilege escalation. Exposing the Docker daemon over TCP without security is the recipe for disaster. Always secure it with TLS certificates. First, generate CA, server, and client certs. Start Docker with TLS using the following command, and then the clients connect with this command. Without TLS, anyone could own your system in seconds. When you run Docker Swarm, services need to talk across multiple hosts. Enter overlay networks. They create a virtual network over all Swarm nodes. Using this command to create a network, then attach services to this network. Containers can now communicate as if on the same LAN, even across servers. It's encrypted, isolated, and critical for microservices. Docker isn't just containers, it's extensible. Plugins let you add features like advanced storage, networking, or logging. Check available plugins with Docker plugin ls, and to install one, Docker plugin install followed by the plugin name. This could let you mount remote directories inside containers via SSH. Plugins are like power-ups. Use them when the built-in features aren't enough. Storage drivers manage how Docker layers your images. Overlay 2 is the default. It's fast, stable, and great for most Linux distros. Other options like ZFS or BTRFS give snapshotting and advanced features, but need special setups. You can check your current driver with Docker info pipe grep storage stick to overlay 2 unless you have a strong reason to change. The Docker CLI is great, but automation loves APIs. Docker exposes a REST API you can call directly, or better, use an SDK like Python's Docker library. We have this Python example. Boom, you've automated container management, perfect for custom dashboards or scripts. Let's talk about Docker BuildX, your key to building images for multiple architectures like AMD 64 and ARM 64. Why does this matter? Because the world isn't just running on x86 servers anymore. Raspberry Pis, M1 or M2 Macs, and ARM-based cloud servers are everywhere. With Docker Builds, you can create multi-platform images from a single Docker file, so your app runs anywhere without hacks. For example, use these commands. Notice platform flag? That's where the magic happens. Combine this with push, and Docker will upload a manifest list to your registry, so clients pull the correct image for their architecture automatically. Think of it as one Docker file, universal compatibility, happy developers. ARM is no longer niche since it's powering Raspberry Pis, Apple Silicon Macs, and even AWS Graviton servers. Docker supports ARM out of the box, but you need ARM-compatible images. If your base image isn't multi-arch, your container won't run on ARM. This is where BuildX from before saves the day. An example workflow. Use Docker BuildX for multi-arch images or pull official ARM-ready images. Bonus tip, QEMU emulation lets you build ARM images on x86 machines. So, the takeaway. If you're deploying to ARM boards or Apple M series Macs, make sure your images support ARM. Otherwise, crash city. Docker isn't just for web apps. It's huge for AI, machine learning, and CUDA workloads. But for that, your container needs access to the GPU. Enter GPU passthrough. With NVIDIA's Container Toolkit, you can run containers with GPU with the following command. That GPU's all flag, it's your ticket to full GPU power inside a container. Perfect for training models or running heavy compute tasks. Pro tips. Install the NVIDIA Container Toolkit first. Limit GPUs per container with this flag. Combine with Docker Compose for reproducible ML environments. In short, if your app needs CUDA, Docker's got your back. Just don't forget, GPUs require extra setup on the host. You know Docker Compose for local dev, but with version 3, it becomes Swarm ready. That means you can use almost the same YAML syntax to deploy stacks in production on a Swarm cluster. Here's what v3 introduced. The deploy key for Swarm-specific features like replicas, update configs, and placement constraints, and native support for secrets and configs. With this example of classic Compose version 3, you can deploy it directly with this command. But it's important to keep in mind that in the latest Docker Compose specification, the version field is no longer required. Compose now auto-detects the version based on supported features. So while older tutorials still show version, modern Compose files just start with services, which is cleaner and future-proof. So Docker Compose now bridges the gap between dev and production, and the newer spec makes files simpler than ever. When deploying services in Swarm, you've got two modes, replicated and global. Replicated mode, you define the number of replicas. For example, 5 instances spread across nodes. Great for scaling stateless apps. Global mode means one task per node. Perfect for agents, monitoring tools, or log collectors that must run everywhere. Think of replicated as scaling horizontally, while global is coverage per node. Pro tip: combine this with placement constraints for ultimate control, like running on only manager nodes or nodes with a GPU. How do containers in a swarm find each other? That's where service discovery comes in. Docker Swarm automatically creates an internal DNS system so services can reach each other by name, no hard coding IPs. Two key pieces are DNS-based service discovery. When you run pingweb inside a container, it resolves to the right IP automatically. AMD Virtual IP, VIP, load balancing, where each service gets a VIP that load balances traffic across all replicas. For example, you have web and DB services. Web just connects to DB colon 3306. No IP hunting, no hosts file magic. So, service discovery makes your cluster feel like one big virtual machine with names instead of IP headaches. You need a reverse proxy for your containers without editing config files every time. Enter Traefik, the modern reverse proxy that integrates natively with Docker. Here's the magic. Traefik listens to the Docker API. When you start a container with labels like this one, Traefik auto updates its routing. It supports HTTPS with Let's Encrypt out of the box. Here's an example snippet in Docker Compose.iml. Spin up Traefik plus your services, and you have dynamic reverse proxying without touching a single config file manually. Perfect for microservices and Swarm setups. If you need a quick Traefik tutorial, check the link in description. Running Docker in dev is easy, but in production, you need discipline. Here are non-negotiable best practices. Use minimal base images, like Alpine, to reduce attack surface. Never run containers as root. Use user in your Docker file. And very important is to enable resource limits. Log to stdout or starr for centralized logging solutions. Regularly update images and scan for vulnerabilities as we've seen before. Production is all about security, observability, and scalability. Nail these, and your containers will thrive under pressure. Want zero downtime? Swarm has built-in high availability, but only if you do it right. The key rule is to always have an odd number of manager nodes like 3, 5, or 7. Why? For raft consensus. Managers keep the cluster state, and if you lose quorum, the cluster is stuck. A typical high availability setup has 3 managers across different availability zones. Workers can be many. Managers handle state, not heavy workloads. So managers are like the cluster brain. Protect them, spread them out, secure them, and never SSH into all of them and run Docker Swarm leave by accident. Containers are stateless, right? Well, until you hit production databases and configs. Here's how to stay safe. For volumes, use Docker run with mount flag to external storage or schedule backups with rsync. For configs and secrets, keep them in Git, encrypted for secrets, or backup var libdocker docker swarm. For etcd or swarm state snapshot the data regularly. A disaster recovery checklist contains volume snapshots, encrypted secrets backup, and swarm manager state dump. Remember, backups aren't optional. They're the difference between a bad day and a total meltdown. IPv6 isn't the future anymore, it's the present. Docker supports dual stack networking, allowing containers to communicate over both IPv4 and IPv6. Why does this matter? because enterprises, ISPs, and cloud providers are transitioning to IPv6 only backbones, and you want your containers to be future-proof. By default, IPv6 is disabled in Docker. To enable it, you modify the daemon JSON file like this. And after restarting Docker, you can create an IPv6-enabled network with this command. To attach containers and test connectivity, run these commands. This enables end-to-end connectivity in modern deployments, particularly critical for IoT systems, Kubernetes clusters, and edge computing environments where IPv6 is mandatory. Control groups, or Cgroups, enforce resource quotas for containers. Docker traditionally used Cgroups v1, but Linux distros are moving to Cgroups v2, which introduces unified hierarchy and more granular controls for memory, CPU, and in and out throttling. To check your system, run this command. For Docker on Cgroups v2, enable it in daemon JSON like this. But why upgrade? Better delegation for rootless containers. Simplified API for resource enforcement. Improve compatibility with Podman, Kubernetes, and CRIO, real-world impact, high-density workloads, machine learning jobs, and CI/CD pipelines benefit from predictable performance and stronger security boundaries. eBPF is Extended Berkeley Packet Filter. It runs sandboxed programs inside the Linux kernel, giving you deep observability without modifying your containers. Tools like Cilium and BPF trace leverage eBPF to capture network, syscall, and performance metrics in real time. For example, to monitor all syscalls by Docker containers, you can run the following command. Why is this revolutionary? Because zero code changes in containers, near zero overhead, and perfect for security auditing, performance tuning, and network tracing. Advanced use case, combine eBPF plus Prometheus for continuous profiling. Visualize latency hotspots, track anomalous behavior, and even block malicious syscalls dynamically. Containers without metrics are blind. Prometheus scrapes metrics, Grafana visualizes them, and together they form the backbone of container observability. Docker provides native metrics endpoints via the Docker daemon. Enable metrics in Docker do this change. To run Prometheus with a config, to scrape Docker, adjust the configuration like this. Then, Grafana consumes Prometheus data for dashboards on CPU throttling, container restarts, and network bandwidth. Add alert rules for anomaly detection and integrate with Slack or PagerDuty. Logs scattered across 50 containers. Chaos. Enter ELK, Elasticsearch, Logstash, Kibana, or Grafana Loki. Both aggregate logs from containers into a central system for search, filtering, and visualization. The default Docker logs are in JSON file driver. To switch to Jelf or Fluent for remote aggregation, run the following command. For Loki plus Promtail, do this. But why Loki? Because it's optimized for labels, like container name, instead of full text indexing, reducing storage costs. Some of the most common use cases are for debugging microservices, compliance logging, GDPR, SOC2, and real-time security alerts. Running Docker in the cloud isn't just about spinning up VMs and installing Docker. Each major provider offers specialized container services. Amazon have ECS, Elastic Container Service, and EKS for Kubernetes. Microsoft have Azure Container Instances, ACI and AKS. And Google have GCP, Google Kubernetes Engine, GKE. Why use these instead of plain EC2 or VM-based deployments? Because they provide built-in autoscaling, integrated logging, and IAM-based security. Best practice, use ECR, Elastic Container Registry, or GCP Artifact Registry for image storage, enable image scanning, and always configure VPC networking for isolation. Key takeaway. Multi-cloud means avoiding lock-in, design your compose, or Kubernetes, YML, so you can switch from ECS to AKS or GKE with minimal friction. Imagine running Docker containers without managing servers. No EC2 instances, no nodes, just containers. That's AWS Fargate, a fully serverless compute engine for containers. The key benefits are no cluster management. It scales per container task and pay-per-second billing. Fargate abstracts infrastructure overhead. You define CPU, memory, and networking, and AWS handles the rest. Pro tip, use IAM roles for tasks, enable logging with CloudWatch, and always keep an eye on soft versus hard limits for CPU to avoid throttling. Key takeaway, serverless containers means simpler ops, same Docker workflow, and they integrate beautifully with microservices and event-driven architectures. Docker images can hide vulnerabilities like outdated libraries or exposed credentials. Docker Hub offers automated security scanning for images to catch CVEs, common vulnerabilities and exposures, before deployment. The way it works is you first push image to Docker Hub, then it triggers a scan, and you get a vulnerability report with severity levels. Under the hood, it uses Snack for CVE detection. The scan checks OS packages, language dependencies, and even base images. Pro tips: always pin to specific versions instead of latest. Regularly update base images and rescan after updates. Integrate scanning into CI/CD pipelines for continuous security. What if I told you most Docker images ship with extra packages you never need? That's an attack vector waiting to be exploited. Enter Distroless images. Google's approach to slim, secure images with zero package managers, shells, or compilers. In new Dockerfile, change the base image from Ubuntu to a Distroless image. The benefits are no shell, meaning no remote code execution, smaller image size, meaning fewer vulnerabilities, and production-only runtime libraries. As best practice, combine multi-stage builds with Distroless images and scan regularly, even if image is slim. Key takeaway: Distroless equals less to hack, less to maintain, and faster deployments. Building secure images is step one. What about runtime threats like privilege escalations or container escape attempts? That's where Falco comes in, a CNCF project using eBPF to monitor system calls in real time. But what can Falco detect? Unexpected process execution, bash in a container, privileged escalation attempts, sensitive file access, /etc/shadow. Falco applies rule-based alerts and integrates with Slack, Prometheus, or SIEM tools for real-time incident response. Pro tip: pair Falco with OPA, Open Policy Agent, for policy enforcement and Kubernetes audit logs for complete visibility. The future of lightweight compute is here, and it's not just containers, it's WebAssembly. With WasmEdge, you can run WebAssembly workloads inside Docker containers for ultra-fast, resource-efficient execution. This is perfect for edge computing or microservices that need lightning performance and minimal overhead. Unlike traditional containers, WASM modules are smaller, faster to start, and inherently more secure. WasmEdge plugs into Docker seamlessly, enabling hybrid workloads, some services in containers, others in WASM. Docker isn't just about OCI images anymore. It's a platform for the next-gen workloads like WebAssembly. Expect this to dominate edge, IoT, and low-latency systems. You've been using Docker for years, but did you know Docker itself is built on an open-source meta project called Moby? Moby provides the building blocks, containered, runk, networking components, storage drivers, and more. Docker Desktop and Docker Engine, they're distributions built on top of Moby. The beauty is that you can assemble your own container platform using Moby components for custom use cases, like minimal container runtimes for edge devices or specialized CI/CD platforms. Key takeaway: Moby equals the Linux kernel of the container world. Modular, extensible, and everywhere Docker runs. When you run Docker run, what really happens? Behind the curtain, Docker relies on two crucial components: containered, which is a container runtime daemon responsible for managing container lifecycles, pulling images, snapshots, and more; and runs, which is a lightweight CLI tool that creates and runs containers according to OCI specs. Here's the sequence: Docker CLI, Docker Engine, containered, runk. Want to bypass Docker entirely and run a container directly with runs? Sure, it's possible. Key takeaway: Docker is not magic. It's an orchestrator built on powerful, low-level tools. Master these, and you can craft custom container platforms without Docker at all. Want to go full container Jedi? Build your own runtime. Why? Maybe you need specialized isolation for high security environments or ultra optimized containers for real time edge workloads. The OCI runtime specification is your guide. By implementing a custom runtime that plugs into Containerd, you can replace Runk with your own. Projects like Kata Containers, which uses lightweight VMs for extra isolation, or gvisor sandboxed containers by Google, prove it's possible. Basic idea is to implement OCI, hooks for create start delete, then register runtime with Containerd in config.toml, and launch containers with double dash runtime your runtime. This is pro level territory. Create bespoke runtimes for security, compliance, or performance optimizations in regulated or high performance computing environments. Modern DevOps has evolved into GitOps, where Git is your single source of truth for deployments. With Docker images and GitOps tools like FluxCD or ArgoCD, you can automate container rollouts to Kubernetes with zero manual intervention. Here's the workflow. Developer pushes code, then triggers Docker build, then pushes image to registry. GitOps tool detects updated image tag in Git repo. Tool syncs cluster state with Git, rolling out changes automatically. This is an example of Argo CD manifest snippet. Key takeaway: Docker plus GitOps equals fully automated, declarative deployments with built-in rollback and auditability. This is the future of cloud-native delivery. Imagine controlling what images can run in your clusters, which registries are trusted, and enforcing security compliance, all dynamically. That's what OPA Open Policy Agent brings to Docker and containerized environments. OPA integrates with Docker and orchestrators like Kubernetes to enforce policy as code. You write declarative rules in Rego, a policy language, and apply them to container operations. For example, you can enforce only signed images can run, or the fact that containers can't run as root, or that certain labels must be present for all workloads. This is an example of Rego snippet for denying latest tags. OPE works alongside Docker authorization plugins, intercepting API requests before they execute. This is enterprise-grade governance for your containers. Docker is no longer just a CLI. It's integrated deeply into developer workflows via Docker extensions. With Visual Studio Code and JetBrains plugins, you can browse images, containers, and volumes from the IDE, or build and push images without leaving your editor, or even debug containers with breakpoints inside VS Code. For example, in VS Code, install an extension, and you can attach a debugger to a Node.js container, inspect logs, and even run Docker Compose commands directly from the command palette. Extensions also integrate with Docker Desktop, bringing GUI-based features for container lifecycle management. Think of it as Container DevX supercharged. Ever wish Docker could write your Docker file for you? Enter Docker Init, the new scaffolding tool for instant project setup. Run Docker Init, and Docker scans your code base, detects the language, and generates a Docker file with best practices baked in, a .dockerignore file to keep builds clean, and optional compose file for multi-service apps. This isn't just boilerplate. It includes language-specific optimizations, multi-stage builds, caching strategies. For Node.js, for instance, it sets up npm install in a separate layer for better caching. In short, Docker init transforms the onboarding process into one command, perfect for teams and CI/CD pipelines. You've heard of Docker Scan, but now meet Docker Scout, the next-gen vulnerability management system. It doesn't just find CVEs, it prioritizes them based on exploitability and context. The features includes image analysis across your org for compliance, integration with CI/CD pipelines for shift-left security, and exploit prediction with AI-driven risk scoring. For example, running this command, it outputs a detailed security report, highlights critical vulnerabilities, and even suggests base image upgrades for remediation. Combine Scout with Docker Hub or private registries for real-time security posture management. Docker isn't just for web apps anymore. It's powering the AI/ML revolution. Why? Containers bring reproducibility, portability, and GPU acceleration for ML pipelines. Some use cases are package TensorFlow/PyTorch models with dependencies, deploy inference services with NVIDIA GPU support, or scale training jobs in Swarm or Kubernetes with container orchestration. This command is an example for running an ML container with GPU. What's next? Docker plus AI pipelines, integrated with MLOps platforms, edge inference with WasmEdge, and lightweight containers for on-device AI. The future is container-native machine learning. And that's a wrap. If you reached so far into this video, you've just leveled up your Docker game from basics to pro-level mastery. If you're building web apps, orchestrating clusters, or diving into AI ML workloads, Docker is your ultimate sidekick. Keep experimenting, keep automating, and remember, containers aren't the future, they're the present. See you next time.